Alright, welcome to the 7th video in this channel, and today we're going to be talking about Newton's laws, specifically the first two laws, the law of inertia and the famous equation F equals to ma. And we'll be discussing the third law in a later video. So, let's jump right into it. Let's first off open up our blackboard, and I'd like to start with his first law. We're going to be going in order. So, his first law, the law of inertia, says that an object that is at rest, let's say there's a ball and it's on a ground, an object that is at rest will stay at rest so long as there are no net forces, there's no net force acting upon it. And this makes sense, right? When you're in your room watching this video or wherever you are, if you were to place any object, so let's say I have my stylus in my hand, if I were to place it on the ground and wait for it to still after rolling a bit, I'd expect it to stay there, right? It's not gonna get like knocked off of the table by some magical force. It's gonna stay there. This makes sense. But the second part of the law of inertia is a little harder to see in life. It says that if an object is moving at a constant velocity, then it will continue to do so forever, so long as there are no net forces acting upon it. And this is harder to see in real life because, if you, this is you, if you were to throw a ball, usually the ball travels in this kind of fashion, right? And then it lands, or your friend catches it, whatever it may be. But generally, it falls, or it stops somehow. Even if you're to roll the ball along the ground, eventually it'll stop, right? Um, but this is all because of other external forces acting upon it. In the throwing case, you have gravity, G, which is pulling it down, and then you have air friction or drag, which is acting on the ball, though it's pretty minimal at whatever at the speeds you're throwing it at. And that's basically just the ball hitting against all the air molecules in the air, and that slows it down as well. And eventually it hits the ground due to gravity, right? And that completely stops it because it can't pass through the ground. And then with the ball rolling, you have friction over there. The grass or the pavement, they all have something that's kind of clinging onto it as it goes, slowing it down until it completely stops. But if you were to say, if you're on ice, uh, I'll do this in blue. There we go, we're on ice now. Okay, if you're on ice and you were to throw a ball here, or roll a ball here rather, it'll slide, right? It'll keep going and it'll go pretty far until it hits the edge of the ice or whatever it may be. But ice is a really good example of the second part of Newton's law of inertia because it's more or less a frictionless surface. It has very little friction. Another good example would be like air hockey. The hockey pucks float on air. This is an air current, and so it goes on pretty fast and doesn't stop. So those are all really good situations, and of course you have it when you're in space. Ooh. When you're in space amongst all the stars. That's obviously a good example of a ball going on forever, because if you throw a ball in space, it'll go at constant velocity. Okay, so that's the law of inertia, and you can see that it holds true. The first part being easier to see, and then the second part you can kind of figure out. But we also have to realize that the law of inertia doesn't always hold true for some people. For example, let's say you're in a bus, okay? You're in a bus or some sort of moving vehicle, and you're starting to speed up after, wait a moment, after you're at a stop sign, right? So you're starting to speed up, and if you're in here and you had some item on the ground, it would actually roll to the back. This is why on planes they tell you that um they tell you to keep all of your valuables on your lap, or like strap it down, whatever it is that they say. They don't want anything on the floor because they know that when the plane starts to speed up and you get pushed back into your chair, and depending on what plane it is, the entire plane seems like it's about to fall apart, or it's really smooth, either one. But you get pushed back into your chair, and everything, if there wasn't anything on the ground, it would all roll backwards. That's because the plane, if I can draw a plane here real quick, this is a plane. The plane is speeding up. And so, these things on the ground, they're actually still kind of following the law of inertia. You see, this plane is speeding up really, really fast. So the ball isn't actually going backwards. Well, it is going backwards relative to you, but as far as the ball's concerned, it's staying in place. It's the plane that's moving along with you. And it's this concept in physics that we call the frames of reference. Frames of reference basically say that, or rather, a frame of reference is like, it's one perspective of looking at a system. Yeah, that's one. It's one way of looking at a system. So, to better explain that, rather than my jumbled mess of words that I just said, let's take yet another situation. You're in a train. This is a train. You've got many windows, and in one of the windows, there's you. Okay? Then there's more windows. Then on the platform, there's a friend of yours. Okay? When the train starts to move off, like this, as far as your friend is concerned, from his frame of reference, the train is moving to the right. Okay? So let's say that it has a positive velocity of 5 meters per second. Yeah, because, usually right is positive in physics and left is negative because of the xy coordinate plane. Anyways, it has a 5 meters per second velocity in the right direction. Okay, so let's label that with R. But as far as you are concerned, from inside the train, and I have to redraw this, so artistic skills coming into play. Here's the window, there's the platform, and you can see your friend out there. And this is you inside the train. Hey, that's not too bad. See? Okay, as far as you are concerned, inside the train, okay, your friend is moving to the left at actually rather yeah, your friend is moving to the right at 5 meters per second at a velocity of 5 meters per second. And let me just double check in my head to make sure that makes sense. Yeah, as far as you're concerned, you're not moving at all. It's the rest of the world that's moving in the same direction as opposed to this guy. Yep, just had to double check a couple of times to make sure my rights and lefts were all in place, but this is what we call a frame of reference. As far as you're concerned, you're not moving, and your friend is, but as far as your friend is concerned, he's not moving, or she's not moving, whatever they might be, and you are. So, depending on the frame of reference, different things will happen. And in the case of, back to the point of not everyone has the law of inertia work for them, well, that's because they're not in what we call an inertial frame of reference. An inertial frame of reference is whenever an object, let's just take you again for this example, is either not moving at all or has some or is moving at some constant speed. So that train uh, situation was actually really good because it showed that in the case of your friend, he was not moving, right? Let's not cut him off. There we go. He was not moving. But in the case of you, you were moving. You were just moving at a constant velocity of 5 meters per second. Thus, you were still within an inertial reference frame. And when you're within an inertial reference frame, you can find an infinite amount of other people who are also within an inertial reference frame. And those are all the people around you that are either moving at a constant velocity or not moving at all. So, this is basically Newton's law of inertia. Objects at rest stay at rest, and objects in motion will stay in motion so long as there are no net forces acting upon them. Alright? Or rather, clarification, objects going at a constant velocity will keep going at a constant velocity, that same constant velocity, because there is no net force acting upon them. And inertial, like law of inertia, only works if you're looking at a situation through an inertial reference frame or frame of reference. Okay, that's his first law done. Now, on to his next one. Let me find some blank space on my blackboard here. There we go. On to his next one, and you all probably know this, the famous equation F equals to ma. This describes a lot of things and is used all over most of high school physics. You have to use this all the time. But what does it actually mean? Well, first off, let's start with units. Mass is going to be measured in kilograms. And acceleration, as we know, is measured in meters per second squared, or this, if you like to write it like that. And because we're multiplying these two units, we end up with force, the unit for force, equaling to kilogram meters per second squared. But this is kind of long and hard to say, also kind of hard to remember. So we shorten it down to newtons, which is written as a capital N. And it's named after, the guy who figured it out. Right, so what does it actually mean, though? What does this entire law mean? It's saying that force of an object is like equal to its mass times acceleration. Alright, that's fine. But how does that help us? And I should probably clarify that it's F net, and we'll get to that later. But how does that help us? Well, I'm actually going to do this. Well, first, let's think of stuff that we can measure, right? Because physics is a science, right? And all sciences, most sciences, require you to actually have some interaction with the real world. Otherwise, all of this stuff, F equals ma, and the magic equation for this x of t equals blah blah blah, that wouldn't make any sense without actual measurements. For example, as I said, or actually I should say not measurements, real life applications. So with this equation, I remember I said that the acceleration due to gravity near Earth is some constant number. It's negative 9.81 meters per second squared in the up direction, meaning it's down, right? And so we can actually apply this equation to objects that are being thrown around near Earth, and we can calculate what their arc is. And with the angular motion one, right? Oh, that's a nice circle. Anyways, with the angular motion one, we can also see it. Like, for example, if you're to have a race car or something, I don't know. I'll do it within the same thing. Say if you had a race car going around this track, what is its centripetal acceleration, or what is its tangential velocity? We can do a whole bunch of stuff. We can measure stuff. But with this, what can we do? How do we define things? Well, first off, we can do acceleration. How are we going to measure acceleration? We take this object that has some acceleration, right? And then we get its distance here. I'm gonna have to draw a bar for this or something, some sort of scale. There we go. We take its distance here, which would be 0. Then after, say, 1 second, and this is, yeah, this is gonna be distance. Distance equals to 0. And then after 1 second, it's here, and distance is going to be equal to some number. We'll say it's d1, and this is d0. So d1 subtract d0 over t1 subtract t0 is going to give us some velocity, right? And then we let it keep going, okay? 2 seconds, then 3 seconds, or not even, just up to 2 seconds, and then we take d2, and we say it's d2 minus d1 over t2 minus t1, right? And this, let me get rid of this cool equation. Sorry, you're cool and all, but you're taking up a lot of space. There we go. There. Okay. Right, and this would end up giving us a velocity. Sorry, just simply a velocity. Probably with a direction. If I were to put my vectors over everything. And then we can call that v1. And then this will also give us another velocity. We can call that v2. And because this acceleration is, or rather because this object is accelerating, we know that v2 and v1 are not going to equal to one another. And we can do is we can take v1, v2 subtract v1 over, I think it's t2 subtract, whatever. We do the delta t for this. My brain isn't working right now, but you get the idea. In the end, we're going to end up with acceleration, and we can actually measure this, right? We can say that, okay, yeah, I'm going to take a clock. Oh, I'm going to take a clock, right? It's got a minute hand and an hour hand. I'm going to take a clock, and I'm going to take some sort of measuring stick. Let's say a really, really, really long ruler. A kilometer long ruler. And I'm going to measure this. And then you'd be able to do this. You'd get acceleration. And then the closer and closer you make these quantities, so 1, 2, or rather like 0.0001 and then 0.0002, right? You'd get closer and closer to the acceleration now as opposed to the acceleration within that big old time. And this is what we call calculus. This is actually why Newton needed calculus. He needed to invent calculus in order to use the equation that he came up with himself, because he was like, oh right, I need an instantaneous acceleration, and in order to do that, he just invented an entire branch of math. Okay, anyways, so we have acceleration, check. Oh, I should probably circle it. There we go, check. How do we define mass? Now this one's kind of tricky, because remember, you could say, yeah, just like we have a meter is defined by this one stick that is at a specific institute, and it's kept in very special conditions so that that is the standard, and you basically create duplicates of that thing to make more meters. So you literally have a stick that is the original meter, and then if you want 2 meters, you duplicate it, and you get 2. If you want a third meter, like a third of a meter, then you'd split it into 3, and then you'd get a third of a meter. There you go. A third of a meter, like that. or if you wanted 100 meters or 1,000 meters. We basically set a standard. So you could be like, yeah, okay, let's set a standard. I'm gonna take some stuff, right? And I'm gonna put it on a scale, let's say. So, let's drop a scale here. You know, this old thing, people used to use it in ancient times to tell the value of something, usually. Alright, so I'm gonna take this stuff and I'm gonna call it 1 kilogram because we're measuring in kilograms. And then I'm gonna take whatever other stuff. Hey, that kind of looks like a dog. Other stuff. And I'm just gonna see how much of this 1 kilogram I need to put on in order to make this thing balance. Right? But you have to remember, this actually does depend on a specific thing which we call gravity. You see, without gravity, no matter what you do, if you still had the scale, without gravity, you could put anything on either side. You could have a huge boulder on one side and then a tiny speck of sand on the other, and it would still balance out. And the reason why I'm bringing up the absence of gravity is because this equation itself has nothing to do with the Earth right now. You just have force equals to mass times acceleration. Nowhere does it say within this equation that, oh, by the way, you have to be on the Earth or close to the Earth in order to do this. This equation is supposed to describe the motion of, or, yeah, the forces that are acting upon any object, on any planet, any non-planet, whatever it may be. It has nothing to do with the Earth. So how would we set a standard for our, mass? Well, we're up in space now, okay? We're up in space, and we're somehow able to breathe. Or maybe we just don't need to breathe. And what we're going to do is we're going to take a spring, and you'll see why in a moment, and two masses. Mass 1, which is going to be a square, and mass 2, which is going to be a triangle. Okay. Basically, we're still going to do the same thing we did here with the 1 kilogram, right? We're going to do the same thing, and we're going to set this M1 to 1 kilogram. So we can write that down in our givens. M1 equals to 1 kilogram. Okay. And we're going to have the spring attach itself to M1, and then we're going to stretch it by some amount x, and then we're going to have M1 in a new spot, x meters away. Alright? Now, I'm doing this because, if you think about it, no matter where you are, a spring will always require the same amount of force in order to, stretch, right? Whether you're on Jupiter or on Earth, it's gonna be kind of hard on Jupiter, what with you being crushed to the ground, but you could still do it. But basically, you could still take the same spring, pull on both ends, and it would still require you, the same person who's doing it on Earth, the same amount of strength in order to pull one end away from the other. So that means that a spring has constant force. And if you're still not sure about that, you can run multiple tests. But let's just go with that this spring has constant force. And what we're going to do is we're going to stretch it by some constant amount so that the force exerted by the spring is always going to be constant, right? So, because if you think about it, a spring that's stretched by X amount will always exert the same force. So force is now constant. We don't know what it is. We still can't measure it, but we know that it's the same force because we still have an intuitive feeling of force. Someone pushes you. You're like, hey, there's a lot of force behind that. Why'd you do that? Right? So we can still feel force, and technically speaking, this should be a constant force. Alright, so we have our quote-unquote 1 kilogram mass. Okay, we've pulled it back by some X amount, meaning we have a constant force, and we're going to let go. By letting go, what we're going to do is we're going to measure the acceleration, because we're able to do that, and we'll get acceleration of m1, so I'll call that a1, alright? Then what we're going to do is we're going to take the triangle, okay? And then we're going to stick it onto the spring. And by the way, this entire example is taken from Professor Shankar. It's an amazing example, and I was trying to think of other ways to come up with my own way of explaining it, but the way he says it is just so beautifully done, I could not figure out another way of doing it. That might be a failing of me, but either way, it's an amazing explanation, so I'm just going to use it. Props to him for that. Alright, so we have this M2. We're going to have M2. Alright, and we're going to do the same thing. It's going to be stretched out so that M2 is going to be in this new position. I'm going to stretch it by the same amount, X. Alright, and these two X's are the same. And then I'm going to calculate the acceleration of M2. And I'm going to end up with A2. Alright? So what I'd end up with is saying that because going off of this law that we're still trying to prove, F equals to ma, right? Because they're the same force, F equals to ma, you can rewrite this as ma is equal to ma, right? Then put into our context, 1 kilogram times A1 will be equal to mass of other thing, M2 times A2, and then you can solve for M2. This is amazing. You end up with M2 is equal to 1 kilogram times A1 over A2. See? And now we have an actual definition for mass in kilograms, or quote-unquote kilograms. It's our made-up kilograms. Okay? Even out in outer space, we're not depending on the gravity of the Earth or anything. All we're doing is using physical concepts of, oh yeah, if I stretch this spring by the same distance, it should technically exert the same force. And you can run many tests to make sure that the acceleration is constant each time with the same mass to double check that. And now you have a definition for m, or of mass, okay? And because we have a definition for mass, we now have a definition for force, because force is equal to mass times acceleration, and we figured out acceleration, we just did mass. So this is a kind of deeper understanding of Newton's second law than I had learned in grade 11, because I have taken grade 11 physics. This is a much deeper understanding, because now I'm not just putting in numbers, I'm actually figuring out where this comes from. Right. And so we can now figure out forces acting upon objects. So if I have any object and I can figure out its mass by doing the spring experiment, okay, if I have any object and it's moving at some acceleration a of mass, I don't know, it's moving at some acceleration a. Oh, I should probably put vectors on all of my acceleration variables, because otherwise I'm technically incorrect in saying that. Yeah, whatever, it's like, we're only considering the one dimension right now. Okay, so I have some object with acceleration a, and now I can figure out the force that is acting upon that object through this amazing equation of F equals ma. So if I have 5 kilogram object accelerating at 2 meters per second squared, I know that the force acting upon it would be 10 newtons. Oh, N, there we go, not M. Sound the same, are different. And now I know that the force that is acting upon it is 10 newtons, unless I'm making some basic mathematical error. Yep, And the way we draw forces that are acting upon objects is through free body diagrams, which basically show arrows coming out of it with which represent forces. So in this case, it's force of applied. So we put force APP, or for convenience, FA. Right, so those are the first two of Newton's forces. I shall be discussing his third. Sorry, these are the first two of Newton's laws. My mistake. And I shall be discussing his third law, which is a very interesting one, in a later video. And yeah.